just a quick recap on the previous topics, primary recovery. So basically we talked about few drive mechanisms, solution gas drive, gas cap, water trap, and gravity drainage. So we pretty much know the importance of drive mechanism that will lead our ultimate recovery based on natural depletion. Okay, so continuation from this topic, we will then go for secondary recovery. This way that we want to boost further from the primary drive mechanism, so we get more actually, but based on certain conditions or features. We'll see later. Okay. So for this topic, the linear outcome will cover three main linear outcomes. The first one, you'll be able to identify a reservoir that needs a drive mechanism. Means that not all might require secondary. The second one, we'll be able to define the right time for secondary drive mechanism. And the third one, to recognize the method to estimate how much volume needed for injection, especially for the water injection. Okay, let's get started. This is the average oil recovery at the plot here. So, based on this one, the question is, what will be the sustained production? What will be the higher recovery? And what's the better economics? Is that having the higher recovery, you will have the better economics? Or you want to abandon your field earlier before you come to the ultimate recovery, because of you want to get the best commercial value. Okay. So this is just to show you that percentage of number of field and cumulative discovery. Okay, discovery in the green one. Okay, talking about 13,000. Here, and number of fields 4,000. Okay. So this is the oil recovery factor for fields more than 10 million barrel or more than 1 barrel in the world. Okay, this is outside the US and Canada, right? Okay. So you can see that the cumulative discovery versus recovery, as you go higher the recovery, right? You can see that the percentage of number fields also discovery also getting higher. Okay. And then these are the recovery factor for all field more than 10 million barrel versus percentage of number of fields. Okay. Essentially, the same. More or less the same drop. Okay. This is just based on different region. Now, again, it's just to show the comparison between different primary drive mechanism. We've seen earlier original reservoir pressure versus recovery efficiency, or RF in this case, RF. Okay, we know that in terms of the recovery, we said that earlier that gravity drainage is the highest now. Although the pressure, original reservoir pressure, right, you can see that is lower as compared to the bottom flux, but still the recovery will be the highest now. Okay. And you can see that solution gas drive and then liquid rock expansion. Okay. Earlier, maybe we just talked a brief about this liquid rock expansion, but in the case that you have very limited solution gas drive, for example, that you have very heavy oil, means that your gas inside your solution will be minimal, right? So that one will be purely governed by the rock or fluid expansion. So that will give the lowest one, this case, less than 5%. Okay. Yep. Okay, this is the reason for low primary oil recovery. It could be due to the reservoir itself, right? For example, you have very highly faulted reservoir. Development plan, it's not optimized. Perhaps you expect different drive mechanism as you drill, and you know that actually it's not that the best plan that we have. Production facilities, like I mentioned earlier, for the gas is highly dependent on the landing pressure. Data inaccuracy, I think it's normal. Although you have abundance of data, right? For example, gas measurement, right? So you have the tolerance, then it can lead to data inaccuracy. So you might, have a problem with calculating your material balance, all those things, right? That can cause of the low primary oil recovery as well. And management. Management could be due to the stakeholder, different stakeholder view. Now we know that like Sarawak, right? Sarawak now we have this set, right? So they manage their own local hospital, right? So those kind of you might have different view of developing certain field, right? Yeah. Okay. So this just to show that like an analog, right? To have the best optimization, we have three interrelated subsystems, which is reservoir, which is PE and geoscience, facilities, okay, facilities engineering, and wells. So it's an interrelated system that we have to work together. Although you know that the reservoir can deliver certain RF, right? By the end of the day, if your facilities are equipped with the right tools or right facilities, you might not be able to fully recover or get the optimum RF out of it. And also, you have wells also here. You might have problem, mechanical problem, all the problem related to the well problem. That also can lead to the lower RF. Okay, so this just to show that like a subsurface from here, as each node that you have a different pressure, right? So start with a reservoir, and then you have wells here, right? Wells, just give an analogy, and then this is a choke at the facilities, and then it goes to the safety point. So it's all interlinked. I would say that, yeah. So that you can have all the molecule being able to fossils. So everything to work together. Okay. Now, just to give you a flavor first, we'll go in details. This is the performance of reservoir with water injection. Okay. So you see that. Here is the water injection, the dotted line blue here, water injection rate, and this is the water production from the reservoir. This is the oil here. Okay, if you notice here, at the beginning, right, before they start water injection, the production starts at 1,000 barrels per day. Okay, as soon they introduce the water injection, you can see that the oil rate start to clear up again. This is where we say that incremental due to the water injection. Okay. So you can foresee that. Remember the one that we've done right from a DCA point of view, right? If you were to establish the DCA line here with the water injection, it's going to be like this. The trending, the oil rate, but because of the introduced water injection, the rate goes up a bit and sustain longer.
So incremental is from the vertical DCA extended one.
This one, yep. The difference here. If you imagine this line and this one, then you have incremental. Yep. Okay. with water injection. Okay. This is just to show you a better perspective. Right? This is the oil production rate. You have primary oil rate here. This without an injection means that purely based on natural lubrication. Okay. So then you introduce the water injection. You can see that the incremental. This way we thought just now. The incremental due to the water injection. Okay. So in this life, in this field life, you can see that as the field decline, right? So you start the injection from point A. Okay, this is we call it the initial field life. Okay, normally within this duration, you won't see the impact of the injection yet because it tried to replace the voidage, the one that you produce, right? You just imagine, right? If you have this room, right? Fill up with the 32%, right? So 5 only go out, and then you have to fill up again. So the room, right, with another 5, right? So same goes here. So that's why the impact it doesn't see it yet. Okay. After that, the point B that where the production start to give impact. Okay, suppose this is should be the production decline period for the primary oil, but because of we introduce motivation, then you start to see the impact of the injection. The rate goes up. Okay. Now the rate will goes up until this peak. After that, the production start to decline as we start to have the water breakthrough. Okay. So the total fluid will be like this, right? But you can see the ratio between the oil and water. Okay, so as you produce, your water cut start to increase more, and then you expect that your oil rate will be lower as compared to the water. Okay. So
based on your experience, ada ke field in Petronas yang sort of mimic textbook punya ni, atau close to
mostly we see this kind of trend. Mostly this is the most trend.
Because macam one of the reservoir kami I-68 you inject, but the support tu you don't see at the nearest well. Support is like you see totally well that's further away. So it's like macam complicated lah for me.
Yeah. In actual, yeah, it's a bit complicated because why sometimes it might not benefit your current well, but it might benefit your infield. The reason why because your wells already not really good location, which you can check, right? You already agree, right? The fix, no more change to this location, right? So that's why you might not see a lot from this existing wells. Once you start to drill in the field, of course you have to evaluate again what will be the optimal location, right? So that's why you see the impact in the other wells. Yeah.
So normally injections is reserve accelerations.
Okay.
Additions.
It's addition.
Addition.
It's addition. Yeah, it's addition. Because without injecting, this kind of profile we have. We say in reserve addition, why? We have
adding a hump on top.
Incremental. It's a reserve addition in this case. Okay. Except you can call it the acceleration if in this you introduce the infield. You want to accelerate further. So in this case, your total volume remain the same, but the profile, the shape will be you bring up front. Okay.
Infield bukan acceleration.
No, I mean it's depend. How say depend? Yeah. If you don't see any incremental of the volume, then will be expression. If you have additional, it will be incremental. Okay. So this is just to show you a figure lah, as a picture that how that works lah, right? So you have the injection valve. I thought there's a picture. No, I'm not check. Okay. Or maybe I click. Okay. Somehow it's not working. Anyway, so this is the injection. Okay, this from the cross section you can see that it's triangular. It's like a, if you have good homogeneous reservoir, you expect that it's like a piston like instrument. You push the water push the oil to the producing. But of course, this is the very ideal case that we have a lot of certification, right? I mean the certification for those things, right? So you wouldn't have this in reality, right? Yeah. So you have the injection pump, and then as you produce, right, you have to spread, because when you produce, as you have a water prep too, you're gonna have water, right? So you have to separate on water for expression there, storage facilities. Okay. Okay. Before we start water flooding or water injection. Okay. So there you need to ask some question. Okay. First question, why you want to inject? Do you need this injection or not? Why? When to inject? What to inject? Right? Where to inject? How much you want to inject? How to inject? And last one, what happens? Okay, this is typical question that we ask before we do the injection. Okay, perhaps we start with the number one. Why to inject? Anyone?
Pressure maintenance.
Pressure maintenance. Okay, so means that if you in the water trap reservoir, do you see the need of injection?
If it's strong, no. If it's slow to medium, maybe you will consider it.
You see the performance of this, right? Yeah, you get the performance. Okay, when to inject? Now you see that you need to inject reservoir, right? Okay, when the best time to inject?
Late life.
Late life.
Mid to late life.
Why?
That is when
you know your reservoir is solution dry. Okay. So you know the pressure will decline, right? Quite fast, right? So you know that immediately know, okay, I need to inject. That's the reason why I need to inject. Okay, but timing wise, when to inject?
when there's no more support from gas statement.
Okay, so it means that you want to produce first and then introduce. Okay. Anyone? Any idea? Okay, our friend here, what I said, we inject after we deplete some reservoir, the pressure, then we inject.
From day one,
From day one. So you make ready your facilities ready. Then turn out to be water dry reservoir. Okay. Okay. That's fine. Yeah. You spend some time with it and then you start inject, right? Okay. For your kids, right? As you dig reservoir and you start inject, remember, you already produce the gas from the solution. As you produce the gas from solution, what happens to the oil? It becomes
bubbling up.
the oil.
The oil becomes thinner. The leaf becomes thinner.
Thinner. Another thing that before that, talking about PVT, the fluid side. What's happened? If you have gas inside the oil,
Yes,
Is it?
reaction.
less viscous. That's viscous. If you produce the gas more, right, your oil start to become viscous. Liquid. So means that it's not good to flow, right? So ideally you want to, as much possible, to keep your gas inside your oil so that you can benefit the mobility of the oil. So that's why it's not good to deplete the gas first and start to inject. And remember, as you deplete the pressure, you want to compensate the pressure. So it means that you have to inject more. A lot of water you inject to compensate the voidage that has been withdrawn. Okay, so it's not maybe a good idea to inject much later. You just to spend a lot of money, that is. And also you might not get the best sweep efficiency. Now come back to Zan just now. You said first day inject, right? There are two things that might happen, right? For your case, you end up with, oh actually we don't need an injection, so we already have facilities for it. Okay, that's one thing, right? Second thing, right? You need to see means that okay, I don't know whether we did cover earlier plot, but there is the viscosity with the pressure as well, because the shape is different, getting viscous as you compress further, right? The shape of the viscosity, that also can happen, right? And also you might be injecting more than your fracture spreading, right? So those kind of things that can happen at the early stage. Okay, so the best time to inject essentially, right? Okay, just slightly above the PB, or we call it the PSGC. PSGC, that the pressure at the gas pressure. But of course, it's very hard to determine PSGC. Normally, we try to target the PB, boiling pressure. Okay, that time will be the most optimum time to inject. Okay. The next one, what to inject? Boiling pressure, or PSGC. Gas critical saturation. That time, gas not mobile yet. That's the best recovery, optimal recovery you can have. Theoretically, yeah, but it is very hard to achieve.
We need to measure from lab.
Yes.
Sample is sample lah.
Because in the field, practical aspect, right? So, because this from the lab, you measure those things from lab, or you do simulation, right? But in the practical aspect, it's a field reality, right? It's a lot of parameters. The outside thing, external thing that you cannot control, right? So it's very hard to get. Normally you go for PB.
But reality, so far lah kan, dah lama pun kita still drill water injector, obviously barunya hilang kan, they are towards the later stage of the life thing kan. Kita still
Do
try lah.
injection, water injection. Yeah. Sometimes we get more data, right? As we produce more, right? So that time, perhaps all our assumption or our methodology based on data available, right, at that time, right? Yeah. So as we understand further the needs of the reservoir, so we have to. That's why that time we have to drill water injection, all those things. But of course, if you were to inject earlier, it could be different configuration, right? So we try to address the current solution, and also towards the shelving life. Okay, how much to inject? 1,000 barrel of water, 2,000. How do we get?
As long as it's not fracking.
Without frac.
Yes.
Okay. Do I stop this from performance? Look up.
Do not disturb.
Easy.
Do not disturb.
Okay.
Small.
Yeah, this one.
Huh?
Conversation with Lisa.
Hmm? Window.
Okay, how much do you inject? Okay, I think first where to inject, right? Okay, before we go how much, okay, where to inject? Where do we inject water injection?
Towards. And what's your producer? The producer. Something.
Means closer.
I mean, normally you inject, you put water injector in the mouth.
Okay.
So that you can inject the oil and it goes
So put in
nearer to your producer.
Put in the aquifer, I mean.
Yeah, something.
Okay. Okay. That's for the pressure. Which maintenance, right? Okay. Do you wear that? Do you also inject in between also? In the column as well? Yes. If you were to address the sweeping problem, right? Okay. If you inject the aquifer, right, it's more on the pressure maintenance. Right? So you are okay with the sweeping. And normally, if you do pressure inject the water aquifer, it will do both basically. Depending on the right injection rate. And also for the sweeping also, mostly you try to sweep the oil, the remaining oil. So maybe the pressure you don't get much because the pressure won't have anymore. So you try to do the sweeping, means that some leftover oil in between, right? You try to target that, get that oil. How much do you inject? Okay, how much do you inject?
Same amount you want to become.
More or less this is the idea. Okay. But we call it the VRR, bodies replacement ratio. I'll show you later. But the idea more or less the one is here. How to inject? How to inject? You want to inject? Where to inject? Somewhere to inject. How to inject?
Drill oil.
Okay, so this is how to inject. Basically, it's just more on the number of wells.
Right.
What's the which area you want to target? And what happened? Okay, now if you have motion model, right? You do the injection, all those things, and then turn out to be not incremental. But you know it's a solution gas drive, but somehow it's not really working well. So what does it tell you?
Wrong model.
Wrong model. Wrong model. Yeah. So maybe could be because of your well placement, right? Sometimes with the old field, like a brown field, let's say barang, right? Barang or the mana, so it's pretty much developed based on the, your well because it's fixed already, right? So you try to come out the best way to apply the secondary method. You still might get the incremental, but not that much that can make it economics. For sure, when you do some injection, right, you will see the incremental. Whether the question is whether is it good enough for you to make it commercially viable. So that's the question. Okay, why inject? Okay, basically this is what we pretty much discussed earlier, right? You can see that okay, is here increasing the amount of alcohol of reservoir, but maintaining the reservoir pressure. Actually, is now we inject the aquifer or sweeping oil with water. This can be done, having a pattern of injection. Okay. So this is the initial condition. You have to see the contact initial condition, and then as you do the water injection, right? So we have small oil in here. Okay, this is where that as the water push, right? You still have SOR level U. This is the residual, all residual due to the water, right? So this one you can recover. Okay. Now, most applicable is the solution gas drive. Okay, so because you know that it's a weak drive, right? So that's why it's the best to apply that water injection. Gas cap drive. Okay, in this case, right, if you have big gas cap, right, you might only require water injection. Okay. But sometimes, like possible like Baronia, right? Okay, you have both. You do water gas injection in the gas cap, and also do the water injection as well. So you will see we sensitize very weak. What's the best the needs for your field? Weak water drive, yes, especially when it is not. Drive. Gravity drainage also will be good for the water injection. Not applicable if you have strong water drive. You don't need the water injection. If you do it, what happens actually? If you still insist, I want to do water injection, so what will happen? Yep. I mean, what happens actually? You might see the incremental, but it won't be sufficient enough to cover the project. Okay, you want to inject? Okay, primary drive mechanical performance. Okay, you this is the where that we need to understand the reservoir characteristic first. Okay, like I mentioned, that reasonable primary recovery solution or we can use for it. Okay, is reservoir floodable? Okay, means that can we build a substantial remaining oil? Okay, you will have incremental oil, but reservoir injection. Okay, so this is the way that I mentioned earlier. You might want to inject at the gas saturation. Gas saturation is greater than SDCR. Is the concept SDCR that I mentioned? Okay, because if the gas saturation is greater than SDC, oil will not form a concentrated band. Means that you might have the fingering impact, which is not optimized for your injection. Okay. So any increase of pressure 30% is enough to dissolve any gas trapped in the oil bank. Means that you can go back to the inside the solution. Water performance resulting from trapped gas is much the same as that obtained with water of increased viscosity. Okay, this is like a polymer kind of injection, right? So if you increase the viscosity, basically you harden the water. Just imagine, it's like a wall, right? You can push easily using the wall to push the oil because you harden the water. But in this case, instead of hardening the water, you use the trapped gas in the solution to have the setting back or effect. Did I confuse you? Okay. Tak faham?
Sekali lagi.
Okay.
Okay. For the displacement, the mobility is very important, mobility ratio. Okay, displacement, right? Okay. So just imagine, this is water, right? This water, this oil, in a tube, right? Okay. If you have a solid surface here, right? You can push easily, like macam pigging lah, right? You can push easily the oil, right? Because you have a solid punya surface here. But of course, I want to exaggerate lah, right? Right. So, how do you make a harden the surface here? By increasing your viscosity of the water. Water become harder lah. Water become harder, right? So you can easily push the oil. Okay. In this case, we're not hardening the oil and the water. Instead, we leverage on this phenomena where the trap gas in the oil, so that you can have same effect at this time. So solution not come out. Gas not come out from the solution yet. It trapped inside the oil. So you will have the same effect. Yeah. Okay. So that's why you don't want to liberate your gas from oil. You want to make it trap as much as possible in your oil. Okay.
So, sekarang tadi you mention about the hardening kan macam tu. So when you inject, ada chemical yang special ke apa?
Oh, that one I'm talking about if you can harden the water if using the polymer injection lah. But here we're not doing polymer injection. It's just that I'm trying to say that we have same effect
from the gas yang
trap. It's improve your mobility ratio. Okay. Where to inject? I think we discussed it, right? Okay. Of course, it's depend your reservoir characterization, right? This way that we talk to each other, right? How does the geological cross section looks like, you know? And then that mechanism also is also important. Okay, aquifer size, right? Okay, this way that we might come back to the geophysics, you know, how extensive your aquifer, right? Okay, good understanding of fluid properties, definitely, and probability of fracture trends. Okay, so what you need to know probability, right? Because let's say, for example, if you have like a probability streak, high probability streak here, right? This is your reservoir, right? Okay, let's use the same thing. Okay, and as you inject here, right? This is the area that you have a probability streak. So what happened if you inject here, right? It's like a freeway into this well. So you might wondering, how come your contact is here, but as you inject immediately, water increase in your or water breakthrough in your wells, right? That can happen because of the constraint you have. So that's why you need to understand if there is any fracture trend or probability streak. Of course, this will be your help, right, to understand better. Okay. Okay, where to inject? So, I mentioned earlier, you are talking about the sweeping. You will have this kind of the pattern. Okay, you have two spot, you know, one producer, one injector. Okay, you have 4 spot pattern, 3 injection. Yes, 1 producer. 5 spot pattern, 7 spot pattern. Yeah, this more on you design your well objective placement to sweep the oil. Okay. Sorry, I'm talking about the inverter just now. This is the procedure, the one that I injection. Okay, what to inject? Okay, you also need to know the source of water. Whether you want to use fresh or saline water or produce water from oil fields. Okay. Sometimes you need to be aware with the clay, some clay that become swelling when it contact with the water, right? So it's might plug. Okay. So in this case, you might to assess injection. We call it hot water. Maybe it's covered in the much later slide. You want to know whether your injection can cause the plugging or fracture. So you need also to assess that one. Okay, what to inject? So these the things that you need to do lah. Let's say you want to know the topographical studies, rock speeds, okay, porosity, turbidity, all those things that you can get it from that. Okay, mineralogy and petrographic analysis, clay swelling that I mentioned earlier. It can cause the plugging. Right? Okay, injection water compatibility, rock free traction. So that you know what to inject. You don't simply just inject the reservoir, otherwise it won't work. Okay. Now, how to inject, right? Okay, how to inject? You might want to use two vertical wells. Okay, you might have already existing producer. You want to convert into the injection or injector, right? And you can do that also. Okay, horizontal wells. You can have also injection horizontal wells, depending on your configuration, your structure configuration. Okay, dump flood. Okay, what's dump flood? Dump flood. Have you heard of that? Dump flood?
Just inject at a high rate for a short time.
Not exactly. Dump flood basically, let's say you have this two reservoir, right? This shape, and this the water, right? Water. This is your reservoir. And you drill, right? Then you make a compression here. This is your compression, right? This is your nozzle. Basically dumping the flood from here into your reservoir. So you get like a natural kind of injection. You leverage on that. Your reservoir.
Yang water tu dari atas.
Yes. Or water from bottom.
Slow lah.
Like that. Yeah. We've done that, some fields in the case of the Bologna. We have in situ gas injection. It's more or less the same like this. We leverage the gas from the other stack reservoir to get the energy. But the problem is, once the pressure equalized, right? So that's a problem now. Then it starts to cross flow. Instead of going to the surface, it's cross flow to the reservoir, which you lose some oil. So when you want to do that, you might want to consider that, in the future, how you want to plug back there this zone. So there are so many ways. Case hole completion, or open hole. Open hole completion of produces prevent shutting off. Okay. It's just that we have to bear in mind that if you're using open hole completion, it might be difficult for you to shut off high water, like this case. Okay. Or for a full section of sand injectors. Okay, this is a technique that we use to calculate how much to inject. Okay, when you can use the volumetric method as simple as this equation. This is very familiar equation, right? This simplification of the G. Empirical method, you can use correlation based on any fields. classical method, okay, you can use the parameter that relate to the reservoir maturity or displacement mechanism. From a curve analysis, it's like a DCA also. You can extrapolate from past performance and reservoir simulation. This is the normal method, and then it's easier to evaluate for the cases, right? You can have different strategy. Okay, now what happened after you inject? So of course, you can see that you look at the desired result. Okay, you can have a better sweat efficiency, and you can arrest in oil rate decline. If you see earlier, right? If you have primary only, the decline will be much, much steeper as compared to what you inject, right? So you want to see if that will happen or not. Improvement in pressure. Remember, sometimes although you improve the pressure, but maybe not so much on pressure. It's more on the sweeping part. Better economics, of course. Even though you have the incremental, doesn't mean that you will make it economics. If it's not economic, means that it's not a reserve lah. Basically, it's not reservation lah. Because reserve is a term of recovery and also the economics part as well. Okay, if there's a result not achieved, what you will do? So you will consider how you want to rearrange your injector placement, your injection facilities, all these kind of things. You want to re-evaluate it. Okay. Remember, I said earlier, VRR, voidage replacement ratio. Okay, it's just that injected reservoir volume over produced reservoir volume. It can be oil, the one you produce, oil, water, and also the GOR. So, VRR, ideally, you want to achieve, if you want to maintain the pressure, what do you expect the ratio to be? 1. Yes. How much you displace, you must do replace with the same amount. Okay. So typically, it's 1. Okay. So, you want to maintain cumulative VRR equal to 1 in order to maintain reservoir at initial pressure. Okay. From day 1, cumulative VRR must be 1. Then you expect the pressure will to maintain as initial. But what if you have instantaneous VRR equal to 1 only, not cumulative? What do you expect? Okay, maybe I give scenario, right? What do you expect from the pressure plot will be? Okay, this is your initial pressure, right? Same time. If cumulative VRR equal to 1, expect your pressure will be maintained. Now, I'm talking about instantaneous VRR. Let's say you start to inject this time. This time that you inject the injection, right? So, of course, pressure will decline because you don't inject yet, right? Then you start VRR equal to 1 here. How do you see? Like this, like this, or like this? A, B, C. B, VRR, instantaneous VRR. Okay. Yes, it will be B. But how you want to get back to this one, to the original PI? What you will do? Yes, in this case, you might want to increase your VRR, instantaneous VRR. But if you calculate cumulative, it could be less than 1, right? Because cumulative VRR equal to 1 means that you're back to the original pressure. Yeah. So you will have instantaneous at 1, but cumulative wise is still less than 1. That's why your pressure is still below than PI. Clear?
So once you reach that original pressure, your cumulative VRR is about 1 million.
If you just maintain VRR equal to 1,
So
you will be flat at this only.
because
Because
your cumulative VRR is always below 1. Right?
this is indication of the below the initial reservoir pressure. Okay? So yeah, that's the okay. This is the one I said earlier to talk about the you need to know that the clay impact, right? All those can cause the plugging. For example, if you do the whole plot here, whole plot is just THP versus cumulative water injection. If you have a good plot, you will have this 45-degree line. But if you deviate from this 45-degree line, you see if it goes up, your well will is indication of the well plugging. If it's below the 45-degree line, it's indicate of the fracture. Means that if you inject, it might goes to other teeth zone, and that time you won't see any. You might not see any incremental. You inject, right? Inject, but why don't improve, right? So it could be because of the you fractured the reservoir and the water goes to the other teeth zone. So basically, this just talk about the planning of water flood lah. Okay, so you need to establish a right teaching requirement, you know, recovery. You want to estimate recovery because of you want to estimate whether it will be viable, commercially viable or not. Okay, mechanical condition. If you to decide convert of the reservoir to injectors, right? Need base infill drilling for injection. Okay, or you want to decide that you need the infill for the infill drilling for injection. Okay, this is will be primary variable of the flood, like the residual observation. I think we discussed a lot this one. Okay, secondary variable affecting water flood, for example, oil, water viscosity, absolute ability. This is the one that we normally get it from the ppm. Structural characteristic of reservoir in the effluent pattern. Okay, this will be the secondary, but mostly you can see that it's related to the fluid itself for the primary variable. Okay. Okay, this is just to show the sweep efficiency. I'll go a bit fast this one. Basically, that is defined that how much you can sweep the dome island. Okay. This is the other sweep efficiency. So because for us, we need to the sweeping efficiency will define RF also. Okay. For example here. Okay. See the oil recovery at the end of the day, this and P is the cumulative you get. So you have the ED efficiency, displacement efficiency, area efficiency, and vertical efficiency, and they multiply with the saturated oil pressure for volume and BO, right? So with this equation, we can theoretically calculate what will be the our NP or recovery of oil. So based on this, or you can estimate from the what will be the our recovery recovery. Okay. So this is just to show you that the gravity effect. Density of displacement fluid lower than density of displacement. You see here, it will be like a tongue over. Displaced density is higher than displacing. Okay. So you will be like a tongue over here because of the density of displaced. Here displaced is higher than displacement. Okay. If density of the replacing fluid higher than density of displaced fluid, this will become over like this. This to inject, right? So most of the injection will go to the bottom because of the to displace, which is here, displace here, is density is lower than displacing. It's just that the gravity effect. I talk a lot, I say the mobility ratio of the sea, right? So this is the equation. You have mu oil multiplied with the relativity of water over the mu water of relativity of the oil. Okay. So what you want? Okay, what will be favorable mobility? You want to have this m is lesser than 1. Okay. You will get the mobility ratio if more than 1, you will have the unfavorable displacement. Means that you will have sort of like fingering like this. Ideally, you want to have like a piston-like displacement, kan? Is right? You want to have like this lah. This is the water, so alright, like this. But if mobility ratio is not favorable, what happens? It will be like this. Kan? So this is your well, your producer. So some part you already produce water, right? You don't want to have that. You might left some oil in between. So that will cause because of the unfavorable mobility ratio. Okay. So as volatility, that's one of the causes that make this mobility ratio is unfavorable. You see here, right? This one that you inject. You see, you have the injection well here. Okay, this connected to this producing well, but some in between, for example, here is disconnect. So for sure, you will not have any displacement in this area, right? So that's why we need to discuss with GNG. So, right? Okay. Now, how we want to overcome this one? Then you put the infill one in between, and then you can tap this area. In water flood management, yes, of course, you have to do the injection well monitoring. Just go fast for this one. Okay. So I think that's for the water flood. I think there's one more, immiscible gas injection. Okay, before I go to the immiscible gas injection, we cover the water, right? Water is, I would say that it's a primary, primary injection that we have in Malaysia, right? Yeah. Any question before I go there? Yes. Yep. Okay, you see here, this one, right? You see, this is disconnect, right? So it means that if you inject, your water injection will not go to this well, because you have the disconnect stratigraphic barrier, I would say that in this case, right? So it will hinder your injection to push, right? By right, you want to get, if you inject here, you want to make sure that the injection can reach your producing well. Otherwise, it's stuck there, right? So to overcome this one, that's why it will introduce the infill, so that when you inject, it can go into this infill. Right?
So
Okay.
this is more on sweeping, right? I mean the one yang nak
Yes.
set tu, itu sweeping lah.
Sweeping.
Lateral.
Yeah. Okay. Okay, it's not that much thing for the immiscible. It's more or less the same concept, immiscible gas injection, right? It's just that for gas injection, you inject in the gasket. Okay, gasket. You just want to enhance the gasket expansion in this case. So it's just like a gas cap drive mechanism, but you just introduce the injection in the gas cap so that you can have better, more energy lah, basically. Okay. So same thing, produce gas rejection into the gas cap for operation maintenance, like I mentioned. Gas injection to prevent gas desaturation with oil due to water drive. Remember, I said earlier, you want to avoid oil column goes into the gas cap, right? Okay. Gas injection into volatile high shrinkage oils, because volatile high shrinkage oils means that you easy to liberate the gas, right? So you want to avoid that. The gas, so the oil liberated your gas further. Gas injection into highly unstable oil reservoir to cause oil swelling or viscosity reduction. Okay. So basically, oil swelling means that it's good because you want to, as it swell, right? It swell, it can go into the producer, right? Yeah. Just macam balloon lah, right? You keep balloon, right? It's become bigger, right? So it can go into the wellbore, the viscosity reduction, right? You don't want to have a very viscous, right? Smaller viscosity means that it's good for mobility, right? Okay, for mechanism, it's more or less right. You have you can maintain the reservoir. You can have the horizontal or vertical displacement. Okay. Okay. Oil swelling, I'm just going to talk just now, right? Gravity drainage. This is more or less the same thing that you have in the water injection. So, okay, the last one. You see here, for gas injection, we inject gas. We have gas injection in the gas cap, the crystal, right? And then you have the aquifer. So you want to have the impact of the sandwich effect. Okay. Normally, for gas injection, we don't use VRR, rather than we use the GIGP, gas injection over gas produced. So you want to maintain what will be the right GIGP that needed for your reservoir. Remember, for the gas, the main parameter is GIGP. For the water injection, it's a VRR. Yeah. Okay. I think that's all.
This one, so
Yes, sure.
GIGP is gas injection over gas produce.
It's a simple ratio. Yeah. But you need to know what is the right GIGP for you. Yeah. So you formulate it through the RMP.
But let's say in this diagram, kita ada OP je, and then ada TI. So kita tak ada gas produce kan, to gauge kan.
Definitely you have because it's a producer. You can have from the oil and social
Oh, GOR lah, macam GOR lah sih.
Okay. Any more question? Perhaps I just ask a few questions to test your understanding the UVM. Just a very simple question Okay. Let's say you have a solution gas drive, right? Okay. So how do you expect that the GOR, the trending looks like? Anyone can draw for me? GOR plot, that's not. How do you expect? I mean, at least don't need to be exact lah.
Then this other point drop,
Okay.
and then we
Go up forever.
go up forever. Yeah, unless kita reflected kita kalau
You go down that, right? Because of the you already have produced a lot of gas already, right? Yeah. Okay, that's good. For the say for the gas reservoir, right? For the gas reservoir, with the dry gas means not dry gas. I mean the without aquifer. It's purely gas expansion drive mechanism. Okay. Typically, how much you expect the RF will be without aquifer? How much? 80%, more than 80%, right? Okay, but what can cause it goes down? Although you don't have water, landing pressure. Yeah, exactly. Because the facilities. Remember, for gas, it's purely depending on your facilities.
kondisi banking.
Concept banking. We don't touch much on that. Concept banking. But since you talk about that, right? Yeah. It's a concept because it's produced, right? Okay. There is the other elements. Okay. Gas, for the oil, you have PB, right? Okay. But for the gas, you have dew point. Dew point is the one that the first drop of liquid will come out from the gas. It's a dew point. Okay. So the dropout in the reservoir can cause the condensate banking. That can also cause your RF reduction in your gas reservoir. Yeah. And condensate banking, sometimes you can flow the gas, the condi to the well. But maybe in your gas reservoir you have very small turbidity. That's why it might start or it's hard to produce. Yeah. Yeah, destructive flow. Yeah, that can happen. But sometimes if you have very good perm, you expect that the gas can push the condi into the wellbore. Okay, so you might question that why is gas, right? You expect higher F, right? But suddenly RT give you low F, right? So probably that is the reason. On top of what landing pressure. Okay, if more question, thank you very much. So we see you next time. Thank you. Okay, Assalamualaikum.
Next time,